let's go ahead and investigate the limit as xy approaches the origin of the function given here. And something else I should probably also note is I keep approaching the origin. There's no reason that we need to do that, but I'm doing it for two reasons. One, it allows us to make our denominators as easy as possible to deal with. I want things in a sense that are kind of undefined when you plug in that 0, 0. Secondly, dealing with x and y going to 0 just is an ideal scenario for thinking about paths. Now, what I would like you to do at this point is to pause the video for maybe 2-3 minutes and just think of several paths. As you approach 0, 0 along the path, x equals 0, y equals 0, y equals x, what do you get? Now that you've taken a few minutes to think about this, let's write down a few details. So what I want to know without going through the work, and I will let you verify this, if you were to evaluate this limit along many different paths, you would get 0. And a few paths in general you might try would be something like the x-axis. So think y equals 0. The y-axis, i.e. x equals 0. Y equals x. Y equals x squared. Or you might say, what about x equals y squared? Along all of those paths, you will end up getting that this limit is 0. But similar to an observation we made in a previous problem, that doesn't allow us to conclude anything. Because remember, this is only 5 different paths. So the question remains, what about the other infinitely many paths? Because all it would take is to find one other path where that limit is not 0. But the question is, how many do we have to evaluate before we're pretty sure? And at this point, even if you just did the first 3 and you got 0 along all of them, because of the form of the denominator, that would give me enough intuition to see if I can show the limit is really 0. And what I'm going to do here is kind of work through some details and make some observations, and then conclude at the end. So the first observation I want to make to go along with this is that if you look at the absolute value, and you'll see in a moment why I want this absolute value, and the absolute value of something is always bigger than or equal to 0. And that's the reason I wanted this absolute value. Now, something smaller than it. So just to give you some intuition, I'm looking to use the squeeze theorem. And with that in mind, note if I would like to get a larger quantity, there's 2 perfectly good ways we investigated doing that in Calculus 2 when we were dealing with our convergence of series and our different tests for convergence. You can make the top bigger, which I have not done here, or you can make the bottom smaller. And a perfectly good way to make the bottom smaller is to simply remove a term. So note kind of the justification. X squared is smaller than x squared plus y squared. So if we just remove that y squared term, dividing by something smaller makes it bigger. And the reason this is helpful is if you take the absolute value of the top, and in the bottom, you don't need the absolute value because it's a square root, but the square root of x squared is the absolute value of x. So this ends up being the absolute value of y. And note this is going to end up giving us exactly what we want, because in a sense, note that as we approach the origin, note 0 goes to 0, the absolute value of y goes to 0. So what we know from our Calc 1 experience is anything in between is also going to be forced to approach 0. So let's write down some details to go with this. So since the limit as xy approaches the origin of 0, the limit of a constant is always that constant, and the limit as xy approaches 0, 0 of the absolute value of y, well, if y is approaching 0, the absolute value of y certainly must be approaching 0 as well. And what this tells us is that by the squeeze theorem, so since these limits are 0, the squeeze theorem implies that the limit of interest, I'm going to say almost the limit of interest, so what we are working with is this absolute value that's stuck in between is equal to 0. And I almost just want to stop here. This really illustrates everything that we need to see, except I want to note that the limit that we've concluded with is not the kind of desired conclusion we want to make, specifically because of those absolute values. But let me remind you from Calculus 1, and we even mentioned it in Calculus 2, if the limit of an absolute value of something is 0, and the key here is 0, that implies the limit itself is 0. So let me write this down and then I'll make that note as well. So therefore the limit of interest, and truly the limit of interest because we're losing those absolute values, is 0. And the property that we are using from Calculus 1 and also kind of Calculus 2 is if the limit as x approaches a of an absolute value of a function is 0, that implies the limit as x approaches a of the function without the absolute values is also 0. And the key is it has to be the limit of the absolute values is 0. And I realize this is a more involved example. It might be something you have to pause and kind of go back to, maybe even look at some examples in the book. So spend some time, work through examples. Note that this is definitely a bit more abstract, but if you have questions, drop me an email, stop by virtual office hours. So stay tuned and take care. Good day and welcome back for our third installment of Limits and Continuity. So in the previous two videos, we were able to introduce kind of the ideas and concepts related to evaluating limits, and we investigated several examples where the limit does not exist. In this video, what I'd like to do is focus in on examples where the limit does exist, and I've actually, if you notice from your note sheet, I've fast forwarded to page 4, and then I'm going to come back to page 3 for the next example. And the first thing I want to note to get going is that all of our limit ideas from Calc 1 still apply. So, and let's even call them limit laws from Calc 1 still apply. Now notice I didn't say Calc 2 because one thing we're going to stay away from, at least when two variables is present, would be L'Hopital's rule. That's something we're not quite going to have an analog of. So in this case of interest, the limit as xy approaches the origin of x squared plus y squared over this quantity. Now, the first thing to maybe try thinking about is what happens when we plug in x comma y. And note, the top is 0, the bottom is 0, exactly as it has been in our previous examples. If we could have plugged that in and got back something that made sense, that would have probably been the value of the limit. Now, instead of going to different paths, which we certainly could do, we're instead going to apply limit laws and Calc 1 ideas. So think for a moment kind of looking at the denominator and our Calculus 1 experience. What is a technique you could use to get started manipulating this algebraically? Yeah, we can multiply by the conjugate over the conjugate. And this was a technique that we saw multiple times when we were in Calculus 1. So the conjugate of the bottom would be to change that minus sign after the square root into a plus sign. And the idea is as long as we do the same thing to the top and the bottom, i.e. we've multiplied by 1 over 1, we do not change the value of the limit. And the power of multiplying by the conjugate over the conjugate is simply how it works out algebraically. So let me note this below. If you were to multiply a minus b times a plus b, that's kind of a simplified version of a and b. What you would come up with is a squared minus b squared, because those middle so-called cross terms cancel off. It's a difference of squares formula. And in this case, our denominator would be that first term a squared. So note the square root just disappears. And then we subtract away the b term squared. So that works out extremely well, and I'll kind of justify that with this asterisk below. So the plus 1, the minus 1 cancel. Now, unfortunately, in the top, we don't get that type of simplification. You have the x squared plus y squared, which is there, and then you're multiplying it by that conjugate term. But even though that doesn't simplify, at least directly, note that the x squared plus y squared cancels off the only term that's left in the denominator. That is, the problem has simplified now significantly to be the limit as xy approaches 0, 0 of the square root of x squared plus y squared plus 1 plus 1. And this is the point where we can use ideas from Calculus 1. Something we've seen kind of over and over again is that we can take a limit and we can break it up over addition and subtraction. So we could take a limit of the first term plus the limit of the second term. And even more so, we can go ahead and move that limit inside the square root. So as xy approaches 0, 0, you have the limit as xy approaches 0, 0 of x squared plus y squared plus 1 plus the limit as xy approaches 0, 0 of 1. Now, the limit of a constant is always at constant. Similarly, as x and y approach 0, x squared and y squared are also approaching 0. So x squared plus y squared plus 1, as we will see in the next video, is a continuous function. But remember, limits are all about doing kind of intuitively what makes sense. If I can substitute in 0 and 0, and I have a quantity that is defined, for us in Calculus 3, that is what we are shooting for. Now, in more higher-powered math classes, I would not make a similar statement. But here, if we can plug things in, it makes sense, we will go with that. So the value of this limit is the number 2. And our takeaway from this problem is that we can apply ideas from our previous calculus experience. So let's build upon this with one more example. And in your note packets, I'm now going to flip back to the bottom of that third page.